Swayam Prabha. Digital India. Educated India.
Good morning. I'm continuing my earlier lecture. Just to review quickly that I was using the method of virtual displacement to generate the equations, and these are all the internal forces and these are the external loads for which I'm going to apply. And note that the support reactions don't matter because the supports never move, so the work done by all the support reactions are always zero. It's only the internal forces and the external joint loads which do any work. Okay, so first I did it putting theta b equal to arbitrary theta b, and then found out another equation applying an arbitrary theta c, and now I'm going to apply an arbitrary delta. Okay, arbitrary delta virtual displacement, and let's see what the virtual the shape of the structure is. This is the shape of the structure, and let's look at what theta AB is equal to delta by 15, theta BA is equal to delta by 15, theta BC is equal to 0, theta CB is equal to 0, theta CD is equal to delta by 15, then theta CD DC is equal to delta by 15, and these are for a virtual displacement delta. So this will be the work done by all the forces here, and let's see what's the work done by the forces. Let us see what the forces are. Okay, we've already seen what the forces are. All the forces are noted here. Note that these cannot do any work. These are always the work done by these are represented equivalently by the work done by the reactions to these loads, so it becomes on the internal side because it's an internal force. Okay, so if I want to write down that equation, I'm going to put it equal to, you have to see what is the work done by the external forces. The work done by the external forces is going to be delta prime into 0 plus 50, that's the force 0 because there is no displacement, plus 250 into 0. So these are all the external forces, plus the reactions are 0 anyway. So the right hand side, the work done by the external forces is equal to 0. Let us see what is the work done by the internal forces. Okay, so the internal forces is virtual work is going to be equal to C. First MAB into delta prime by 15. Note that both of them are anti-clockwise, so it's positive. Then work done by MBA into delta by bar by 15. So that's the real force undergoing the virtual rotation. Then what can we say about MBC? Well, theta BC is equal to 0, so that's going to be 0. Then the work done by MCB, theta CB is equal to 0, so that's going to be 0. Then we have MC D undergoing theta CD virtual, so that's MCD. Then we have MDC multiplied by its rotation, so that's the work done. See, these are all the work done by all the moments. Now let us find out the work done by all these forces. Okay, so if you look at it, what's the work done by those? Let's see. Let's take 20 by 3. 20 by 3. What's the work done by this 20 by 3? The displacement of this point is 0. So the 20 by 3 does 0 work. What about the 40 by 3? You will see that that point is displaced by 1 in this direction. So the work done by the 40 by 3 is negative, because 40 by 3 and the displacement delta are opposed to each other. Now let's find out the work done by this 60. There is a reaction also, so that's why it's on the internal side. 60, the vertical displacement is 0. Work done by the 40, the vertical displacement is equal to 0. So there's no work done by those. Okay, so essentially, if you look at it, what am I left with? I am left with that internal virtual work is equal to MAB by 15 plus MBA by 15 plus MCD by 15 plus MDC by 15 minus 40 by 3 into delta is equal to 0. Okay, so this is what we get as our equation. Okay, now note one particular thing that we have. So the work done by these. Okay, so this is the equation that we get. Okay, and now if I substitute, if I put this in, one of the points that I would like to make over here is that here, if you look at it, so now this is the equation. So this equation, if we plug in all, anyway, let me just put this into a standard format: MAB plus MBA plus MCD plus MDC minus 15 into 40 is 600 minus 200 into delta is equal to 0, because I've taken the 15 on the other side. So what we get, and since this delta prime cannot be 0, we get that MAB plus MBA plus MCD plus MDC is equal to 200. This is my other equation that I generate from the third. Now note the advantage of this procedure. Remember how we obtained it the last time? The last time the way we obtained it was that we actually found out the reactions and then put the reactions equal to the loading that was applied on the structure, and based on those the whole procedure, that's how we obtained these equations. Okay, here just by applying the virtual work equation without actually looking at any kind of equations of equilibrium, okay, we generated this apparent equation of equilibrium. Note that this equation is actually really a virtual work equation. Okay, it's a work equation. Only thing is that it gives you something which looks like a moment equilibrium equation. And these three, if you which solve simultaneously, you will get theta B, theta C, and delta. Okay, So much for all of this, and you will see that this equation is identical to what we had got last time. Okay. Now here, this is the concept of the application of the principle of virtual displacement. So I just want to go back and review what I have done before I proceed. What I have done is I have introduced a new concept of using a theta. Okay, the slope reflection equations, I've used a simpler form of the slope reflection equations where all you have are the rotations and the fixed end moments. The only point here is that the rotations are defined from the chord rather than from the original position, original tangent. Okay, so from the chord to the tangent, to the displaced tangent of the elastic curve. This is how we define the new thetas, and once we defined those new thetas, we saw that we got exactly the same equations that we had got earlier without considering this new definition, the original definition of theta as well as delta. Okay, and finally I showed you the application of the method of virtual displacement in obtaining the equations. This method of virtual displacement essentially becomes very important when we have to write down the equations corresponding to a displacement quantity, because the only thing that we get directly from the slope deflection equations are actually the moments, and all other shear forces etc. are derived quantities. And to write down a force equilibrium equation, we have to actually go through significantly large number of equations to get that one equation corresponding to a displacement. By using the method of virtual displacement and putting external virtual work equal to internal virtual work and writing down, noting that the fact that work is a scalar, so you can add up the work done by all the forces acting on the individual members and sum them up, we got an equation very easily without having to go through several equations. This is the advantage of the method of virtual displacement. Okay, so now what I am going to introduce you to is a couple of other problems, and I am going to again introduce the concept. See, one of the very important aspects of using the displacement method is that you saw that we have to draw the displaced shapes corresponding to each degree of freedom, so that we can find out what the member end rotations are related to the structural degrees of displacements corresponding to the structure degrees of freedom. Okay, so now what I am going to do is I am going to introduce you to a couple of problems where all that we do is actually just look at how the displacement pattern comes and relate, just see if we can relate the member end rotations to the structure degrees of freedom, then you can write down the member end moments as in terms of the structure degrees of freedom, and then you can use virtual displacement to write down the equations. Okay, so essentially this becomes a very simple procedure once you get the kinematics. You see, this is called kinematics, because when you want to find out, given a degree of freedom, given a displacement corresponding to a degree of freedom, how does the structure displace? This is called kinematics. Okay, so that's what we are going to concentrate on, because once you do that, the displacement method becomes very, very simple to apply. Okay, so let us now look at a few problems. Let me now take you through to some complicated issues, not as simple as they looked last time. So let us take. Note that here also, if you assume axial rigidity, there are only 3 degrees of freedom, and the 3 degrees of freedom are this, this, and this. Identical. All I have done from the previous problem is I have taken this straight member and I have inclined it. Okay, and let's put down some values to it just to satisfy ourselves. I'll make this equal to what would I do? Let me make this. This is 3, 4. Okay, so I'll make this 9. Okay, I'm going to make this 12 and make this 15. Okay, so essentially this is A, this is B, this is C, and this is D. This is 9 meters, 15 meters, 12 meters. Right now, all I'm interested in is what happens when I give this equal to 1, this equal to 1, and this equal to 1 independently. That's all I need to draw. I'm not interested. Once I know that given a loading, I can always find out everything else. Okay. So right now we are going to concentrate only on kinematics, because you will see that kinematics is important to relate, to get the member end moments due to the displacements corresponding to structure degrees of freedom. It's also important because those become my independent virtual displacement patterns. So you see, this is what is known as I'm using the same displacement patterns that I generate for each individual degree of freedom, because I know that if I choose one degree of freedom equal to 1 and the other degrees of freedom equal to 0, they are each going to be independent, because that is the whole definition of independent degrees of freedom. Okay, so in other words, I could have actually chosen completely different independent deformation patterns for the virtual displacement and been absolutely correct. The only problem is that to figure out two independent displacement patterns is not as easy as it looks. However, since my degrees of freedom are independent of each other, I know that if I take one displacement equal to 1 and the other displacements equal to 0, I am going to generate a pattern which will be completely independent when I take another degree of freedom equal to 1 and the others equal to 0. Those are going to be independent, and that is the reason why I choose those patterns as my virtual displacement patterns. If you could figure out 3 independent, for this there are 3 degrees of freedom, so if you could figure out 3 independent virtual displacement patterns, okay, you could actually write down 3 independent equations. Okay, I myself am very, I'm not that thing in terms of trying to figure out what would be an independent pattern, and therefore what I tend to do is I tend to use the simplest independent patterns that I can generate, which are the displacement patterns corresponding to the degrees of freedom themselves. So that therefore you see how important the displacement pattern becomes every time, and that's why the kinematics. So here I'm going to first put theta b equal to 1, and note that when I put automatically I am assuming theta is equal to 0 and delta equal to 0. I don't need to explicitly state it. See, this one is actually not a problem. The inclined member does nothing to the displaced shape. So this essentially, if you look at it, theta AB is equal to 0, theta BA is equal to 1, theta BC is equal to 1, theta CB is equal to 0, and of course theta CD and DC are equal to 0. So I could relate it. Okay, so I'm going to put them down. Okay, So this, if it was real, these would be real. If this was virtual, these would be virtual. Okay, I mean identical. Okay, then let me put theta c is equal to 0. And once I give theta c equal to 1, okay, you have to be consistent. So therefore, let me put down what? This is theta BC. Theta CB is equal to 1. Theta CD equal to 1. Theta. Note that these are all thetas being taken from the chord to the tangent. All of them from the chord to the tangent. But remember, I told you that when you put thetas, the chords are the undisplaced direction. So there is no change. Now for the interesting one. And let me draw this. And for this one, I will use a different colored pen to highlight to you what actually happens. Okay. Now note that what am I doing? I'm going to put displacement delta equal to 1. If you put delta equal to 1, okay, what happens? This member, since this is moving perpendicular, there is no change of length, so there is no problem. So this is going to remain. Like this. Let's look at this member. This member, for it not to change its length, along which direction can it move? It can only move perpendicular. Please note that, again, these are small displacements. So the perpendicular movement does not increase because, ideally you would say arc, but when you have small displacement, an arc and the tangent are the same. So this can move along this direction only. So therefore, you see, and what about this member? This member, since this end has gone here, the only way, this cannot change length. So therefore, you have, this is already gone by 1 from here to here. So this was the member. Okay. Now how will this member move without increasing its length? Only if it was perpendicular. Okay. Now look at where this point goes. Okay. If this member was not there, this point would move here. But since this member is there and it is fixed at this point, it can only move along this line. Now if it can only move along this line, okay, since this point now has to move because it cannot be here. This point is not on this line. So if I moved only up to here, this would increase this length. Okay, so therefore this now has to move. Okay, so when it has to move, how does it move? Well, it moves perpendicular so that this member does not change length. So the whole point here is that since axial rigidity is there, nothing can change its length. And so the only, where would the point go? The only way is where these two lines intersect. So this is the point where it would go. So how would it look now? Now the thing is that see, theta b is still equal to 0. Okay, so this point cannot go anywhere. So this would still be perpendicular to this. What about this? Since theta B is equal to 0, this would still be parallel to this. This would be parallel to this, and this would be parallel to this. Okay? And here this would be parallel to this. Okay? So that entails, that ensures that theta B is equal to 0 and theta C equal to 0, which is what you need. Okay? So now if this was 1, because delta is equal to 1, how much is this? Now let's see what this is. If you look at this particular one, this is the angle theta. Okay? So if that is the angle theta, okay, and this is perpendicular and this is perpendicular. So which angle is represented over here? If you look at it by similar triangles, this would be the same as this. Satisfy yourself. Okay? So then, if you look at this, this is 12 and this is 9. Okay? So therefore, 12 by 9, since this is 90 degrees, okay, and this is 90 degrees, okay, 12 by 9 is tan theta is equal to 12 by 9. So here also tan theta is equal to this by this. So what is this equal to? This upon this is equal to 12 by 9. So you will see that this is equal to 9 by 12. 9 by 12 is 3 by 4. If this is 1 and this is 3 by 4, you will see that this is equal to 5 by 4. Okay? So now, once I have drawn the shape, now the point is to find out theta AB and theta BA. And here I need to connect. Whenever I have a displacement, I need to connect the chords and take displacement, rotation from the chord to the tangent. So if I do that, what do I get? If you look at it, from the chord to the tangent. Okay? And what is that? You will see that this displacement is 15, because 12 squared by 9 squared, square root is the hypotenuse, and that's going to be equal to 15. So this is 12, this is 9, this is 15. And 5 by 4 is the displacement here. So 5 by 4 divided by 15 is this rotation. So this rotation is equal to 5 by 4 divided by 15. So if you look at that, that is equal to 1 by 12. Okay? So if this is 1 by 12, similarly here also this is 1 by 12. Let's look at this one. This is 3 by 4, and what is the dimension? The length is 15. So 3 by 4 by 15 is equal to, this angle is equal to 1 by 20. Similarly, this angle is 1 by 20. Similarly, over here also we have to join the chord, the the 2 points of the 2 ends, and join it by a straight line. And so what is this? This is delta, and what is this length? 12. So this is 1 by 12, and this is 1 by 12. So having written those down, this is from the chord. So what is theta AB? Theta AB from the chord to is anti-clockwise positive. So this is 1 by 12. What is theta BA? Theta BA is equal to, from the chord anti-clockwise, so 1 by 12. What is theta BC? Let's see. From the chord to the tangent clockwise, so it's negative 1 by 20. Similarly, CB is negative 1 by 20. From the chord clockwise, so theta CD is equal to 1 by 12. Similarly, So this one, if you look at it, this is fairly complicated, okay? And that's the reason why I've spent so much time actually drawing. Now you see this is equal to delta equal to 1. Up till now, what I did was that, these were simple problems, and so now if I looked at inclined, you actually have to spend a lot of time figuring out where each point goes. Once you know where each point goes, you can then draw the displaced shape, because delta equal to 1, theta b is equal to 0, theta c equal to 0. You know those. So from that you can draw the displaced shape given delta equal to 1. This is the displaced shape if delta is equal to 1, and once you have delta equal to 1, then that means this is that this is equal to 1/12 of delta, 1/12 of delta minus delta by 20 minus delta by 20. So that's the overall concept, and then you can write down theta AB is equal to 0 into theta B plus 0 into theta C plus 1/12 into delta. So that means essentially theta AB is equal to delta by 12, and then you can substitute in the equation and you can get your expressions, for MAB, MBA, MBC, MCB. So you see, once we have this, you can see that this kinematics gives you all the equations for MAB, and then these are also independent virtual displacements. So these can then be used to actually write down your equations, the virtual work equations. Okay, so much for the equilibrium. Now I'm going to make one thing. I'm going to introduce you to the kinematics of various kinds of members, because once you know the kinematics, you can actually write down the equations for any kind of structure. Okay, so let me now look at another equation. I'm going to take this same thing, and I'm going to say that now this BC member is flexually rigid also. So if member BC is flexually rigid, let's draw this. So same equation, okay, and A, B, C, D. Now this member is flexurally rigid. What happens when the member is flexurally rigid? Let's see. How many, so we first find out the degrees of freedom. Okay, 1, 2, 3, 4. So unconstrained degrees of freedom are equal to 3 into 4, 12. How many restraints? Restraints are equal to 2 into 3, because both of them are fixed. So 3 restraints per joint. So that's minus. And then constraints. How many constraints do we have? See, one constraint is actual rigidity of all the 3 members. So that is 1 into 3 members. Now in addition to that, BC is also constrained to be flexurally rigid. Now remember, I had said how many for flexural rigidity for each member? 1 member and 2 constraints. So how many constraints do I have? 3 plus 2, 5. How many degrees of freedom? 1. What is the degree of freedom? I'm going to take it as this. Okay. Now so note that what has actually happened is that because of this being flexually rigid, now you see this member cannot rotate because this cannot rotate. Okay. And here also it cannot rotate. So theta B and theta C both have disappeared as independent degrees of freedom, because no way can this joint displace. If this joint displace, then this has to go this way, and there is no way this can go, because then for it to be rigid, this point has to go and violate. Okay, so you can see that. And similarly for theta C, if this rotates and this rotates, this has to come down here, and it will violate this thing. Okay, so there is only 1 degree of freedom, and for that 1 degree of freedom, I have to draw the displaced shape. So let me. It's the same, so 9, 12, and then 15, 12. Rigid, and this is rigid, so it can only deform linearly. Okay, so let us see what happens here. This is very interesting. See, note that this point is going to go there. This point is going to go there because delta is equal to 1. Okay, and I have already shown where this point is going to go. This point is going to go here. Since this is gone by 1, this is going to come down here. This point is going to be here. This is 1. This is 3 by 4. The points go exactly where they went earlier. Okay, the only difference that happens is, now how are these points connected? Note that since this member is rigid, this member is rigid, the only way these 2 points can be connected to each other is if in a straight line, because this is the only way that member BC can deform. It can only go straight. Now if it goes straight, now what happens? Let's see. What is the angle here? 3 by 4 by 15, that's 1 by 20. Now note that means this also has rotated by 1 by 20. Now the interesting point here is that since this member has gone this way, there is no way that this tangent can remain in this way. Why? Because you see that will violate the continuity of the joint. Okay, so that means if this rotates by 1 by 20, this also has to rotate by 1 by 20. The tangent at this point has to rotate. So how will my displacement of this look? This will look like this. And here again, this was this way. There's no way it can. So this also has to rotate in this fashion by 1 by 20. So it's going to look like this. So you see, what has happened is, if I were to plot this, now this is how the thing has rotated due to delta. So now let's see what my member end rotations are, and for that I have to draw again. This one I don't need to draw. Okay. Okay. These are the chords. So now once member BC is rigid, okay, if a member BC is rigid, its slope deflection equations are no longer valid, because MBC, if you look at it, MBC will be given by 4EI upon L into theta BC. Okay, but what is theta BC? 0, because it cannot rotate. It cannot rotate. Okay, so therefore, you see, theta is from the chord to the tangent, that's 0. Okay, and when it's rigid, EI is infinity. So therefore, essentially what you have is, you have a 0 by 0 situation, Okay, so therefore the MBC and MCB can only be obtained by actually equilibrium at the joints. Okay, that's all. There's no way. So therefore BC does not come into the picture at all. But what about AB and CD? These are flexible members. So these slope deflection equations have to be written. So you need to find out from the chord to, what is this? This is going to be the same as 1 by 20 if you look at it. Okay, 5 by 4 divided by length. What's length? 15. So this is going to be 1 by 12. Okay. What about this? Well, let's see. What is this angle? From the original to the chord is going to be the same as 1 by 12. So from the chord to the tangent is how much? It's 1 by 12 plus 1 by 20. Okay. Here, from the chord to the tangent, what is this? 1 by 12. Here, from the chord to the original undisplaced tangent is equal to 1 by 12. What is from the original tangent to the new tangent because of this rotation? That is 1 by 20. So what's the total? From the chord to the tangent is equal to 1 by 12 plus 1 by 20. So let us see what theta AB is equal to. Theta AB is equal to 1 by 12. What is theta BA equal to? 1 by 12 plus 1 by 20, which if you look at it in terms of 60, 5 plus 3, 8 by 60. 8 by 60 is 2 by 15. So it is 2 by 15. This one I don't need to find out because I cannot write down slope deflection equations for this. So this is going to be equal to, DC is going to be equal to 1 by 12 and CD is equal to 1 by 12 plus 1 by 5, that is 2 by 15. So these are the member end rotations in terms of delta. Okay. So here the point that I was trying to make is that the kinematics of the structure is very, very important, and once you can draw the displaced shape corresponding to each degree of freedom, you are well on your way to using the displacement method for solving any structure. The advantage of the displacement method as you see it is that it actually makes life much easier for you in general. Now I'm going to actually take this particular problem, this problem, okay. I'm going to take this particular problem and I'm going to actually put some loads on it and see what happens in reality, okay. So let me take a very simple load initially. Let's not complicate the issue too much, and let me say that this structure is only subjected to 20 kilonewtons, and due to this 20 kilonewtons I need to draw the bending moment diagram for this particular structure, okay. So I have got these. So now from these what do I get? This is a single degree of freedom. So from this what do I get? I'll draw the equation, write down the equation. Theta AB is equal to delta by 12. Theta BA is equal to 2 delta by 15. Theta CD is equal to 2 delta. Wait a minute, I made one mistake, and that is that we didn't find out what the values were. Let's go back here. If you go back here, from the chord to the tangent anticlockwise, from the chord to the tangent anticlockwise, from the chord to anticlockwise, from the chord to, so all of them are positive, okay. So actually I can write them down. Delta DC is equal to delta by 12. So now I'm going to substitute this into my equation. What are my fixed end moments? See, since there are no loads in the members, okay, fixed end moment is equal to 0. Okay, so what is my MAB? All my fixed end moments are 0. So what is MAB equal to? MAB is equal to 4 EI, and AB's length is 15 times delta by 12 plus 2 EI by 15 into 2 delta by 15. Okay, so if you look at this, what does this become? This becomes 1/3, so this is EI upon 45. Okay, and if you 3, so this is going to be equal to 5. So this is going to be equal to number 45. So 5 plus 9, so this is going to be 9 EI delta upon 225. MBA is equal to 2 EI by 15 into delta by 12 plus 4 EI upon 15 into 2 delta by 15. So here I have 6, so that's I need to go to 450. So this is going to be equal to 5, and this is going to be equal to 120. So 80 and 160. So this is going to be 5 into plus 160 EI upon delta. Okay. So if I divide throughout by 5, I get 35 upon 90 EI delta. And same way I can find out MCD. You will see that MCD will be equal to 35 by 90 EI delta, and MDC is going to be equal to 9 EI delta upon 225. Okay, so I have obtained these equations in terms of the delta, and then I need to write down the virtual work equation. So how will I write down the virtual work equation? Find out all the work done by all the internal forces undergoing the displacement. So what is external virtual work? External virtual work is delta prime into 20. And what is the internal virtual work? Internal virtual work is going to be equal to MAB into 1 by 12 plus MBA into 2 by 15. Of course, delta remains, this is going to be delta, this is going to be delta, plus MCD into 2 by 15 delta plus MDC into 1 by 12 delta. Okay, so this is equal to this. So from this, if I put it in, okay, I'm going to get that this implies that 20 is equal to MAB by 12 plus 2 MBA by 15 plus 2 MCD by 15 plus MDC by 12. See how easily we got the equation. If you had to actually do it by this thing, what would you have to do? Well, you'd have to find out all the moments. You would have to actually solve everything, find out all the reactions, and from that, from the shear and the axial force, you would then get the horizontal, and then equate the horizontal reaction that these two equal to 20. It will take you a few hours to do that. Okay, satisfy yourself, try it that way, and you will see that you will get this equation. Now here you will see that all these are in terms of delta, so I'll substitute these values in. I'll get only one equation in delta, and I can solve for delta. Once I solve for delta, I can immediately plug it back in here, and I get MAB, MBA, MCD, and MDC. So in other words, once I solve for it, I can get MAB. So now I know MAB. Okay, I am not solving them, but I know MAB, MBA, MCD, and MDC. These are evaluated. Okay, these can be evaluated. Okay, by plugging it into that equation, solving for delta, and then plugging them back in here. Okay. Now once I know, see, I've only found out MAB. What about how do I draw the bending moment diagram? And this is where equilibrium, again, you cannot forget equilibrium. So what you have to do is, you have to do this. You cannot forget equilibrium. Equilibrium cannot be violated. Okay? So therefore, if you look at this, this is MAB. This is MBA. This is MBC. We did not evaluate MBC because BC was rigid. But nonetheless, even in a rigid member, you're going to have bending moments. Okay? Remember that. So, MCD and MDC. Okay, MCD, MDC. So these are my bending moments where I know this, I know this, I know this, and I know this. Can I find out MBC? Sure I can. How? Equilibrium. Equilibrium says that MBA plus MBC is equal to 0 since there is no moment applied. Similarly, over here you will have that MCB plus MCD is equal to 0. So you can actually evaluate this and this. Once you know these, since there are no bending moments, there are no other loads on the members, just the bending moments themselves, you can find out the reactions and draw the bending moment for the structure. Okay? So you see, the whole point here is just to go back. You can draw the bending moment. I'm going to leave that to you. I've already found out what MBC. There are no member end moments, so you can always find out the reactions, and then the bending moment diagram will look like this. Straight line here, okay, continuous straight line here, come here, continuous straight line here, this way. This is your bend. And that you've got the bending moment diagram for the load of 20 kilonewton force. Okay. The point that I'm trying to make here is what are the important aspects to the entire thing. The important aspects to this is A, finding out the number of degrees of freedom. Identifying for the degree of freedom, let's come down here, you will see that for the degree of freedom, get the displaced shape of the structure. The displaced shape of the structure can be obtained through kinematics. Please keep practicing this. Okay? You have to get kinematics. Once you get the kinematics, you've got all the thetas, member and deformations. Once you got the member and deformations, you can get the member and then apply the same delta as my virtual displacement pattern, and so I can write down my virtual work equation, and from the virtual work equation I can actually substitute these and get an equation for delta from where I can solve delta. Once I solve delta, I plug those back, get MAB, MBC, and then use equilibrium to obtain your bending moment diagram. I hope over the last couple of lectures I have been able to impress upon you that how the method of virtual displacement becomes a very powerful tool in simply solving analyzing a frame by displacement method. Thank you very much. I shall continue by actually solving a few more problems so that you can gain confidence of how to actually use the displacement method and the method of virtual displacement together. In fact, the method of virtual displacement is used to generate the equations. It's not a separate method. The method is the displacement method in which you generate the equations to solve for the displacement using the method of virtual displacements, and once you solve them you can get the member and moments, and once you know the member and moments in any member, it becomes a statically determinate structure and you can draw the bending moment diagram. Thank you very much. Look forward to talking to you, continuing with you on using the displacement method. Bye.